computer. Okay, and now let's hope. Let's hope that this will work out. Okay, so well, thanks everyone for joining today. So maybe just a little bit of introduction. So my name is Claire. I'm a group leader here at the University of Tübingen. I've been here for about 2 years or so, and I work on reinforcement learning, but from a slightly different perspective than maybe Georg has been presenting so far. So I work on reinforcement learning theory, and in particular, I try to understand how exploration works in reinforcement learning and how we can make exploration work in a way that so that the algorithms are more efficient. So I'm going to try to clarify all those things today by introducing what is this optimism principle that is in front of, that is the main title of this lecture. And yeah, so let's just get started, and let's just first clarify what is this problem with exploration. So far, this is lecture 4, lecture 5 of this RL class. So I'm assuming you're already familiar with MDPs. So in MDPs in general, you start you have an MDP like this, and it can be some sort of graph. I don't know. I'm just gonna make it could be something like this. It could be like this. Well, and these transitions are randomized and they depend on the actions that you take. And sometimes when you take an action, you get a reward. So maybe here the rewards, the rewards are a little bit bigger here than here, right? But you start here, and in general in reinforcement learning, you try to find a policy that's going to navigate in this environment and try to collect the rewards. Okay, so the problem of exploration that you probably have already seen in previous classes is that typically if you create an algorithm that is going to explore here and observe this reward here, maybe it's, so let's assume that, for example, there's noise. So this is let's say it's a reward that is centered in some small value and with some sigma square, from some randomness plus minus some noise. And same here, it could be some randomness. It might be that you're lucky, right? That you start from here and you cross here, you observe a reward that's actually quite large. So I'm going to call it R plus. And then, you start from here and somehow with the same policy, you end up going like this, and you have an R, which is something like R minus. Well, so far, if you don't introduce more exploration, you might just be happy with the policy that you've tried so far. You might just be happy with this policy that goes most of the time here and had observed this small reward. Whereas a policy that would actually go more often here would get, with higher probability, would get higher rewards. So let's say that this is policy pi1, this is policy pi2. What I've just described is a situation where we can model it kind of equivalently. We can model it like this. I am in the state S0. I have a policy pi1 that has whose reward in expectation, the reward, I'm gonna call it whose reward is smaller in expectation than the reward of the policy pi2. So what I've just said is that perhaps, this is like a lesser or equal, but vertical one. But so this policy pi1 has an expectation, has a smaller value than the policy pi2, but it takes a while before you actually discover this. And you need to explore these policies. You need to explore your environment enough to actually collect this information and, significantly say, yes, okay, policy pi1 is worse than policy pi2. So policy pi2 is better. And in RL, it's even more complex, right? It's even more complex because at every state, I need to take potential actions that are not rewarding. Like when I take this action, I am not observing any reward here. But like deeper into the MDP, I might observe a reward long-term that also depends on all the randomness in the dynamics and of the environment. So this problem of deep exploration is really hard. But, you know, at the simpler level, you know, even in this kind of modeling here, just saying I start from S0 and I have a collection of like a few policies that I could try out, and they have different rewards with different probability distributions. How can I balance my exploration across the policies to find out what is the policy that has the largest reward? Does this story so far make sense? I'm assuming that you already heard of exploration before. I think actually what you heard of is epsilon greedy. Yes, I see nods. So we're going to talk again about epsilon greedy and see, like, have a look at it from a different perspective and maybe discuss whether it's a good idea in general or maybe whether it can be improved. So, like, part of this class is actually to kind of come back on this idea of exploration you've seen so far and you know, propose an alternative way of looking at it. All right, so our program today is the following. First, I'm going to introduce this problem that is called bandit algorithms. So bandit algorithms are algorithms to solve exactly the problem that I just described, this problem of having several options and having to deal between, like, to manage exploration and exploitations between actions. So I'm gonna specifically describe this mathematically. And then so I'm going to give you two bandit algorithms. And then in the second part of the class, perhaps the last half hour, roughly, we look at how we can use these principles, this optimism principle and this exploration principle in reinforcement learning beyond bandit algorithms, because bandit problems are a thing, but you know, like most problems out there are not bandit problems, though there are some out there that are interesting. But so for you, perhaps it's interesting as well to see how we can use these principles in reinforcement learning to do exploration. So I will talk about AlphaGo and AlphaZero, which are algorithms that build on these upper confidence bound algorithms. And I will kind of quickly go over other ideas in potentially deep or, you know, in general in reinforcement learning and deep reinforcement learning that use these exploration principles to improve exploration. I am more than happy to take questions. I will repeat the questions so that they go through the recording that I'm trying to, I hope it will actually, you know, work out. I'm going to turn this so people see my face in the recording. Otherwise, why am I recording? All right. And yeah, so I'm really happy to take your questions. Like, feel free to interrupt me. Yeah, we have time. Okay. So most of this course, at least the first half, follows a few chapters of this book that's called Bandit Algorithms that was written over the past few years by Tor Latimore and Csaba Sepesvári, who used to be my colleagues for the 4 years I spent at DeepMind, like, yeah, a couple of years ago. And it's just great. So like, if you have any questions about bandits, or if there are things, if you want to follow up on some things in the class, like, this book is just great. So there's, you know, all that I say is in the book and there's more in the book. So the bandit problem is kind of the one that that I've described before, but we're gonna kind of put different words on it. So now my policies will be called arms. So this comes from a time when people were still going in casinos and pulling the arms of the machines. And when you pull the arm of a machine, it creates a random variable, which is essentially, you know, whether you win or not. So we can model it as a binary or the Bernoulli random variable, but it can be another random variable. And so these arms are going to be your actions. So like, you know, in at time t, like at every time t in my learning process, I will be able to pull an arm. So this arm here, it belongs to, you know, I should write it like this, right? Okay. So I pull one of these arms, and when I pull an arm, I generate a random variable from this machine. So this is this phenomenon here. There's a random variable, like this, also a noisy observation that comes from the machine. And that gives me an information on my, on the potential, on the environment I'm dealing with. And at time t, at time t plus 1, I have a history of observation. So I have the actions I've pulled, the rewards I've observed, along the time. So for each of the previous times, I know what actions I've pulled and I know what rewards I've observed. It's like in my little exploration problem. I know which policies I've tried and I know what rewards I've observed. And the question is, what is the action I should choose at time t plus 1, given this information? So this, I can call it, if you will, I can call it pi of ft, the policy of my agent at time t, like given the history. And my goal is to build a policy, so to build an algorithm to maximize the expected sum of the rewards. So I'm going to play with this environment. I'm going to pull t times arms from this casino, right? And I want to pull the arm more often that has the largest expectation. So I haven't written that yet, but it might be in the next slide. But typically, for each new, yes, it's here. So like this is saying that the expectation under new A of the reward is mu A, right? All right. So far, so good. Okay. So we said we want to maximize the reward, the sum of rewards. But, there is only a finite number of arms here, and there is one of them that has a larger probability of winning, or larger probability of winning than the others, or rather a larger expectation. So we're going to call it A star, which is going to be essentially called my best arm. It's, out of my pool of policies, my pool of strategies here, my pool of arms, there's one of them that's best, is the one with the largest mean. And so it makes sense, instead of trying to just maximize the sum of rewards, like here we know what would be the best, right? So it makes sense to instead minimize the difference between what I would have gained by always pulling this best action, meaning t times the sum of rewards. So this is this thing here, right? This is the best possible reward I could have obtained if I always did the best thing, if I knew the means. And this here is the sum of the rewards of my strategy. So instead of maximizing this thing, I'm going to minimize the difference. This is just a renormalization, if you will. It's just saying, you can maximize as much as you want. You'll never do better than that. So now we're going to measure, instead of just measuring how much reward we gain, we can actually measure how fast we get to optimal. And I'm going to precise this. We're going to see why this is the case. So the first thing we want to think about is, why does this metric make sense? Why do we minimize regret? Or why is it interesting to look at the regrets rather than like just the sum of the rewards? So perhaps we can think together about a better equivalence definition for the regret. Like, let's try to rewrite this thing in a way that uses the number of times I've pulled arm A and the gap, meaning the difference between the value of arm A and the value of the best arm. So let's look at this quantity of RT. So what is this? At each time t, I pull only one arm, right? So there's only one, like this thing, it comes from a certain arm, right? That it's 80. So, and it's one arm in 1K. So what I can do, and I do nothing, if I do this, I am not adding anything, but I can always say that this is the sum for over the time steps of the sum over the arms of the indicator of AT equals A, R, T. Does that make sense? Yeah. I've just summed over the arms, and I've just, essentially, there's only one of these random variables that is true at every time t, right? So I've just added a lot of zeros in every time steps. All right, and now essentially what I can do is I can invert this sum. So I can sum for A1 to K of sum, sorry. Yes, we're gonna do this. The expectation of the sum for T. Okay. All right, but so now I've simplified the problem a lot, right? Because in this expectation here, this thing, we know that arm A, you know, this sum is only, this variable is only true when arm AT, the arm I pull at time AT is actually arm A, right? So now I'm summing over all the arms and I'm filtering out the time steps when I put arm A. So now this random variable, we know that its mean is mu A. We know that if we would pull the expectation inside, we would have mu A. So this is called the tower rule of the conditional expectation. We can essentially pull the expectation inside if we carefully do it. So we can always, you know, take the conditional expectation and take again the expectation of those things. But essentially you start seeing that, I'm gonna push this, what is going to happen is that this quantity here is essentially the sum over A of mu A times the expectation. So here I'm just gonna write a little ... because I didn't do the job completely. So I skipped one step here, but like I think it's intuitively you see it. The sum over T of the times I pulled arm A. Sorry, it's a lot on the right, but the next slide will be not my handwriting, so it will maybe be easier to read. And this is the number of selections, so the list NA of T. It is the sum of over T of the times the number of selections of arm A. So here I exactly have expectation of NA of T. Does that make sense? Does this derivation make sense? I see some nods. Yeah. All right, so this exact same thing is written, you know, with LaTeX in the next slide. So it's a little easier to read, but essentially you recognize exactly my derivation, right? We take this expectation on the right side, and you know, we pull the mu star and the new mu A that we have isolated. We pull them together, and now we have this mu star minus mu A, and this is exactly what I call delta, the gap between, you know, the gap between arm, the best arm, and the arm I pulled. And then I get the expectation, the number of times I pulled arm A. But so the final expression is this thing. And you know, when you think about it, you know, I just proved that the total regret is just the sum of the losses that I incurred from each of the suboptimal arms, from each of the arms, multiplied by the number of times I pulled this arm. It's not, you know, it's not rocket science here, but it requires to, you know, manipulate things a little bit carefully. And I end up with a metric that actually makes sense. I'm going to, over time, measure, you know, how much loss I get from each of these arms, right? And the goal now is to create an algorithm that is going to pull these bad arms, the arms with large deltas. So when delta A large, I want to, pi should not pull it. Pi should pull it little. So we don't want to pull too much arms with a large gap. So that's why this metric makes sense. It introduces this notion of costs of exploration through the gaps, but it also allows me to measure the speed at which I will converge to the best strategy, which is to pull always the best arm, by like how much I will pay before I reach, a regime where I pull the best arm most of the time and I accumulate a reward that is actually something like mu star t. And so how long does it take me to get there? All right. This I just said. All right. So just keep this. The first, yes, there's a question. That is, okay, that's a very good question. All right, so if you wanted to compute this quantity, you kind of need to know mu star and mu a for all the arms. All right. So not great. So we don't want, look, our algorithm cannot rely directly on computing the regrets. We're gonna have to go through other ways, like through the examples, like every time we pull an arm, we're going to get some information about this arm that is going to allow us to estimate what is the mean, what are these mu a's. But in the back, my system that knows the means, it can evaluate me. So me, I don't see the true means. I can only see samples. But my system that is evaluating me, it can measure my regret. And what I want to bound in theory is what is my system? What is going to be my score? What is the score that my system behind me is going to compute for me? So it's kind of this loss, but I cannot observe this loss. I can only observe the reward that I get from the arms. Exactly. So this is the exact right intuition. So I cannot observe the arms. I cannot observe the true means, so I need estimators. And so the first strategy is to construct an estimator by just pulling each arm once. I get a sample from each of the arms. I get the highest, I take the highest sample, and then I pull this arm until the end of time. So this is the greedy strategy. So it's the one that, that I described at the beginning, and that's that, you pull this policy and you obtain a reward, you go for it like all the time. This is, we know it's not a good idea. And we can actually prove it on, it's in math, usually what you do when you want to prove that it's not a good idea is you find a counterexample. So here, we designed a counterexample. So a counterexample is very simple. You take two arms. So you have two slot machines and they have Bernoulli distributions. So the Bernoulli distribution gives you either a 0 or a 1, and it gives you a 1 with probability mu1 or mu2. So this is the mean of the distribution. So if I pull each of these arm once, so here mu1 is larger than mu2, but there's still a large probability that the sample from mu1 is 0, that the sample from arm1 is 0, and the sample from R2 is 1. That can happen. And that actually happens with a non-zero probability. We can actually compute what is this probability is this. So 1 minus mu1 times mu2. So after I've pulled each arm once, if I continue pulling the best arm until the end of time, I can already tell you that like the number of times I've pulled arm 2 is at least this number. So this lower bound, this probability of error, or of like making a mistake, times t minus 1, which is the rest of the time so far. So it's quite easy to construct a counterexample for greedy, right? Like noise, randomness can fool you into following an option that actually has bad rewards if you look at it, or like that has a lower expectation. So we need to add exploration. So far, I think I haven't said so, like on this problem here on the greedy, I'm pretty sure you were aware of this, or at least you can intuit this. So now epsilon greedy was introduced to you as like this idea that with probability epsilon, you're going to take a random action. So whatever you know so far about the means, you're gonna just take a random action and observe a random reward from one of these arms and update your estimators. And with the rest of the time, with probability 1 minus epsilon, you just pull the best arm, the current best arm. So this thing here that I denote mu hat A is what? Is the sum over S equals 1 to T of the indicator that I pulled arm A times the reward that I got at time S divided by the number of times, well, I can just write it like this because now we're familiar with this notation, the number of times that I've pulled arm A. Okay, so it's just an empirical average, right? So in epsilon greedy, when you pull arm A, you observe a reward, you basically update this estimator, like this, update mu hat A of T, right? You got a new reward, you update your belief or like what you think about this arm. And then you continue exploiting like this. And the question is this a good idea? Well, so the problem with epsilon greedy is that over the time, you're always going to pull one of these bad arms with a non-zero probability because it's a probability epsilon, right? That is non-zero. And we've said that like the regret, we've proved in the previous slide that the regret is the sum of the arm times the number of times that I've pulled this arm. Okay. So now we can look at this quantity. And for all the bad arms at the end of horizon T, we know that this quantity is at least epsilon times T in expectation. All right. At every round, there's a probability, epsilon over K. At every round, there is a probability epsilon that I explore. And if I explore, I pull arm A with probability 1 over K. It's the uniform strategy. So for all the bad arms, there's a non-zero probability that I explore them until the end of time. So this allows me to prove that like the regrets of epsilon greedy is always bounded by this linear term here that is, this is, well, epsilon times K minus 1 over K. It's the probability of pulling a bad arm. The minimum cost of pulling this bad arm, but it's still non-zero because it's a bad arm, times T. So what I'm saying now is that if you do epsilon greedy, you're always going to continue accumulating losses, even if you have enough knowledge to stop pulling these bad arms. But just by the mechanism of epsilon greedy, you continue accumulating these losses. You continue pulling these bad arms that you could stop pulling, if you were doing something smarter. What can you do to kind of fix epsilon greedy? Is there any idea? Like, can you, or are you familiar? Have you tried? Yes, there is. decay epsilon. So that's a very good idea. Actually, it's even it's an existing idea. Like people have proved that it's a good idea. You could decay epsilon by something like k over t. So if you decay epsilon in a hyperbolic way like this, you decay epsilon, then you can prove that the regret of epsilon greedy is actually bounded, it is not linear anymore. The problem is that to tune correctly this schedule here, it's not exactly k over t that you need to obtain the bounded regret. It's k over delta mean square. This is this result. So this comes from this paper. I'm not going to do the proof today because the proof is a little involved. So I think that will probably kill us at this time of the day after lunch. So let's not do this. But like, you can prove that the actual schedule you need to guarantee bounded regret depends on the minimum gap square. And that comes back to the question we had earlier. We don't know the means and we don't know the gaps. If we would already know the gaps, if we would already know the losses of the arms, the problem would be solved, right? We would not have to do exploration. So you can play around with epsilon. And, in practice, I think I would really encourage you, whenever you play with epsilon greedy, to try and decay it in something of the order of 1 over t. But the true value that you should put in the schedule, you cannot have, because this true value depends on a problem-dependent quantity that you actually don't know. So we need a better idea. We need something that is actually going to allow us to trade off exploration and exploitation in an adaptive way that does not depend on any knowledge of the problem a priori, or minimum knowledge of the problem a priori. In the assignment, you will implement epsilon greedy, but instead of making you implement the epsilon t greedy, like the schedule, which you can implement in Beam, I guess, like it's very easy. But like I make you implement this alternative strategy that's called explore then commit, which is essentially the equivalent of epsilon greedy, but where you do all the exploration at the beginning. So you do you pull each arm m times, and then you stop, you commit to the best empirical mean, and you pull it until the end. So it's kind of, all this exploration that we sprinkle in epsilon greedy, we do it at the beginning, and then we exploit. And for this algorithm, we can also prove regret bounds, and we can do all sorts of things that I think in the assignment, there are a few hints on how to do this. But yeah, so in general, even for explore then commit, there is not a good way of tuning this exploration in a way that does not depend on the problem-dependent constant. So we need something better. And this something better is going to be this optimism principle. Any questions so far? All right. So the general idea of the optimism principle relies on a tool that we call confidence intervals. So these are intervals around an estimators that quantify our uncertainty on the true quantity that we are trying to estimate. So for those of you who are more Bayesian-minded, you can think of it as the quantile of your Bayesian posterior. If you have the lower and the upper quartile, they kind of contain a large mass of your posterior distribution, so they are giving you a notion of uncertainty or confidence. But in general, the confidence interval is this kind of interval that we know that the true mean of the arm that we're trying to estimate is somewhere in there. And we want to know that the probability that the true mean belongs to this interval is larger than something very big, something very close to 1. We want to find functions like LCB, lower confidence bound, and UCB, so the two extreme values of my interval. I want them to be designed in a way that I know that, you know, the mean, the true parameter I'm trying to estimate is inside. And so in general, what this gives me is like an algorithm or, you know, a principle like this, you know, at a certain time t, I'm going to be able to estimate. So these are my arms, you know, this is this drawing here. There are 4 arms. The true values are the little squares. So this is mu A, you know, the little square here. And I don't have colors. Do I have colors? Yes. Okay. And these red things are the mu hats. This is mu hat 1 of t. This is mu hat 3 of t. Okay. So, and this is the UCB. And the general principle is going to be to say, these confidence bounds, they define the set of worlds that are plausible given my current knowledge. I've only observed this amount of samples from the world. I don't know what is the true world, but they're not all the worlds are admissible out there given my current knowledge. There are only a finite set of worlds that are still okay, that still correspond to my data. And out of these possible worlds, there is one that is better than the others, the one that has higher rewards. Yes?
Bound 0 and 1 or the like, small side lines?
Yes, so the bounds are this thing. So this is, yeah, this is LCB of arm 4 at time t, and this is, yeah, exactly. And this is UCB of arm 4 at time t. So the intervals are like this. So these are the, you know, the rewards. The mu's are in between 0 and 1. And now, you know, I have 4 arms. So I put them next to each other. And these 4 arms have different means. And for each of them, I got rewards. I got samples. And I can estimate these confidence intervals. That makes sense? Okay. And so the optimism principle just says, it's very simple, that given this uncertainty, you should act as if you were in the best plausible world given your current knowledge. So meaning that like the best plausible world for each of these arms is the world where mu A, so mu1 is here. And this is still plausible, right? This value is still within my confidence bound. So this is the highest possible value for arm 1. And for each of these arms, I have a highest possible value. And then I choose arm A. So my action is just going to be the arm that maximizes the value in this best possible world. Okay. So now what we need is to actually define these things. So far I haven't given you the actual, you know, functions for LCB and UCBs, but these functions are actually fairly simple. So, you know, it's not going to be too hard. Okay, so let's see. So the first tool we are going to need is how do we control, you know, this uncertainty. So we're going to use for this, we're going to make some assumptions. So, I mean, I guess some of you are familiar with this, the idea that like for random variables, you know, not all of them have expectations. Some of them have what we call heavy tails. And when you have heavy tails, you don't even have an expectation. So like all these things, all that I've said so far doesn't mean anything. So we're going to restrict our world to nice distributions that actually have an expectation, and even stronger, they have a variance. And we're going to assume that the variance is actually like the tail of the distribution is bounded by Gaussian tails. So I'm allowing my arms to have distributions that can be not Gaussian, but that look like Gaussians, or at least are bounded by some Gaussian with variance sigma square. So this is just to guarantee that my sample, when I pull an arm, I cannot observe 10 million, you know? It's like if the mean of my arm is 1, I cannot, there's the probability that the actual reward is 10 million is virtually 0. It's not 0, but it's virtually 0, okay? And this allows me to say that if I have many samples from this distribution, and I try to estimate the mean, this empirical average is actually going to concentrate around the true value of the parameter. And for those of you who know the central limit theorem, which says that, you know, if you do that asymptotically, you actually, you know, the law of this empirical average converges to like a Gaussian with mean mu a, something, you know, I don't know. Okay, so like this is just the asymptotic version. In general, we can always say that for these nicely behaved random variables, we can always say that through Hoeffding's inequality, if you have f samples from a distribution, so this is like the empirical average for s samples, the probability that this mean plus some bonus is smaller than the true value mu. This is actually, you know, decreases, the probability decreases exponentially. So what am I saying here? I'm saying that I have my true mean here. And let's assume that I'm observing a Gaussian distribution. It's always hard to draw. Okay, so what I'm doing is, let's say I'm observing these samples that they look relatively like Gaussians. I'm going to estimate mu hat with the S samples. The probability that if I add mu hat, if I add x, some x here, so this is if I add plus x, this is mu hat s plus x. If I add x, the probability that this new thing here is smaller than mu is relatively small. And the reason is because this mu hat is going to be very, very, very close to mu very, very quickly. And this is true for like all these distributions that behave well like Gaussians. So that's the notion of concentration inequality or like deviations that is very important for all this optimism principle. And in the tutorial just after this session, you're gonna get to, you know, play around with this and actually, you know, try to compute what is the right x that I should put here to guarantee that this probability of, you know, not estimating correctly my upper confidence bound is bounded by delta. So the probability that my confidence interval is indeed, you know, with high confidence. So this is what we wanted, right? We want this. We want to guarantee that if you design well your UCB, your interval, the confidence interval covers the true value with probability 1 minus delta. All right, so you'll do this small calculation, but overall, you know, what is going to happen is you're going to find something like this. You're going to find that if you add a bonus that has this form, square root of 1 over number of times you've pulled the arm times some logarithm of a sequence of delta t that you will find. So this delta t, you can think of them roughly as like delta t as t to the 1, t to the minus 3, meaning that 1 over delta t is equal to t to the 3rd. So it's a weird 3. So this is what I just answered this question here, how to choose but like, I don't want to spend too much time on this. But like what you're going to find in the tutorial is that you can define exploration bonus that have this form, square root of some log t divided by number of times you've explored the arm. So this means the more you've explored the arm, the less you need a bonus to explore, and the more, like the less you have samples from this arm, the more you need to pull it, or the more you'll be pushed to pull it because the confidence bound will be very large. So yes, so that's, you know, summarizing an algorithm like this. So this is UCB. UCB just says, yes, there's a question over there. Yes, okay, here. So this, I say that I want to choose a sequence of confidence levels so that the sum of the probabilities is bounded by something like a constant. So essentially what I say is, over my entire horizon, you know, I'm going to pull a lot my banded arms, and every time there's going to be like a UCB. Over this entire horizon, I would like that these intervals are almost never violated. If I, you know, I don't want to kind of at each time accumulate a certain amount of risk that I'm making a bad decision. I want that my intervals are always covering the parameter with high probability. And this probability here, you see, like essentially it's very small. The probability of making an error is very small. And that's why, this is why, you know, this is why I want this sum to converge. I want the sum of this series to converge. Yeah, I want the sum of the probabilities to be finite. In all generalities, I could allow it to be something very, very small, like a square root of log t or log t, or very, very small quantity that grows very, very slowly with time. But like, I think it's simpler to think of it as like, I don't want to make mistakes, or I want to make a finite amount of mistakes when t goes to infinity. Yeah. So that's how I end up with this type of algorithm that just exploits, you know, this confidence bounds to force me to explore. There's been research on this for a very long time, and there are lots of, you know, people that proved regret bound. They proved that the regret of such an algorithm can be bounded depending on the parameter alpha that I put in this square root. And, you know, typically, if I should show this video, but just I want to show you the regret bound. So if you tune alpha well enough, in a way that actually guarantees this coverage in, you know, this constant coverage of the number of mistakes, then you can prove a regret bound that basically says that the expectation of the number of times you've pulled a bad arm is bounded by log t, so that's very small, times 1 over, or like some constant over delta square. So I want to, this is important. So like the cost, like the amount of time that I'm going to pull this bad arm will scale with the 1 over the gap square. So if I have a gap, I have an arm that has a very small gap, I'm going to need to pull it a lot to kind of manage to distinguish it from the best arm, right? It's going to take me a lot of samples before I can make sure that it's not the best arm. But if the gap is very small, then it doesn't cost me too much to explore this arm, right? In the regret, the cost of this exploration is actually very small, so it doesn't matter too much, right? But still, the number of, you know, mistakes grows with 1 over gap square. But it grows only with log t, and log t is very small. Log t is a very, very slow growing function. So this is a pretty strong result. Any question on this? Okay, I'll just, in principle, I have, let me see. This is how to come here. Here I am. This is the figure that I just showed before, but this is the, so I'm gonna show. Yeah, so this is this figure. I think in the recording they won't see it, but it's okay. So the same figure, the UCBs and the LCBs, and we're gonna see UCB in action. We're gonna see what UCB does. And so every time, UCB pulls an arm, I add a count in the bottom here. So at the beginning, I've pulled very little, all these arms. The arms are Bernoulli. So I only see zeros and ones, but that doesn't make any difference here. The laws are bounded, so it's sub-Gaussian. So all the hypotheses of my theorems are valid. And what is going to happen is this lozenge, or this kind of square, or the true values of the arm. They are the true values of the arm. So this arm in the middle is the best arm, and the second best is this one. And what we're going to see is how much is UCB pulling the bad arms. So do you see what's happening to these upper confidence bounds? They're slowly aligning to the value of the best arm. And every time there's one from a bad arm that kind of slowly grows over the one from the best arm, it's pulled, and it takes it's decreased by a large number. It's decreased suddenly. I think we see it again. You saw this arm was just pulled, and my confidence, of its mean decreases again. And so the reason why they grow slowly is because in my square root, I have a log t. So they grow very slowly at the speed log t. Right. And they grow very slowly. And overall, at the end of one random trajectory of this algorithm and this Bernoulli problem, what I see is that the best arm has been pulled the vast majority of the time. And this is exactly what we want, right? We want to have exploration, but just the right amount. Like not something that's proportional to t or anything, just the amount that allows me to figure out that this bad treatment of this bad arm is actually bad. Okay. I think I just have to go back to the meeting. Right. So like I said at the beginning, for the Bayesian-minded people in the room, this idea of, drawing something like saying, okay, this is not very straight. The idea of saying, okay, I have, my true mean mu, and I'm gonna just create an upper and lower confidence bound that, any value in here has the same probability. It's just the whole interval covers the true value with high probability, but there's not one of these things that is more likely than one of these values that's more likely than others. It's a little weird. If you have more information about the distribution, typically if you know that your arm has a Gaussian distribution, well, very likely, if you've observed this, at this time step, with that amount of observation, you have a posterior distribution that's something like this, And so, okay, it's true that like this covers, like I said, if you take the quantiles, like the large quantiles of this posterior distribution, you will cover the true value. But you can use this posterior belief you have on the true parameter, and you can use it to measure your uncertainty and to control your exploration. So this Bayesian algorithm is called Thomson sampling. The idea of Thomson sampling is to say that if you give me a prior, like that's your choice as a practitioner, if you give me a prior and I give you samples, then you can compute a posterior distribution like I just did here. And using this posterior, you can kind of get some random estimation of the mean of the rewards. Okay, so the idea of Thompson sampling is to say, okay, at time t, I have a posterior distribution. This notation here is the posterior. The posterior can be computed as a function of the prior and the likelihood. I'm guessing you're familiar with Bayes' rule. And if you have a posterior distribution, what I suggest you do, or what Thompson sampling suggests you do, is to sample a mean according to current belief you have over the distribution of your arm. So you sample a potential mean, and then you act as if the true environment was the one that you sampled. So for each of the arms, so if I have two arms, let's say, in my little drawing that I had earlier, so I have arm one, I have arm two, and now I have like a posterior like this. And for this arm, I have a posterior like this. So I have two posterior distributions for my two arms. I'm going to sample. So let's say I sample like this, mu tilde 1. And I sample from this high variance distribution, maybe I sample here, mu tilde 2. We don't know. Maybe this arm here, maybe this arm is worse. We don't know. But right now, my belief doesn't allow me to conclude on this. So I can sample from from both distributions. I obtain two worlds that are compatible with my current observation, my current belief. And I'm going to act not optimistically, I'm going to act in this environment, in this sampled environment, which you can call hallucinated, which is a word that like Bayesian people use a lot. So in this hallucinated world, you can just pull the action that has the largest mean. You obtain a new reward from this arm, and you update your posterior. So this arm, the reward that you obtain allows you to update your posterior, given that not your current posterior, which is now the prior of the future distribution, right? So like my current posterior gets a new observation that I can process into the posterior and get a new posterior. So it's super easy, at least on paper. The issue is, in general, computing these posterior distributions and sampling from them is hard. There's only a few cases that are well known and for which you can do this. So typically Gaussians, that works out. If everything Gaussian here, we know how to do it. If things are from the exponential families, we know how to do this as well with our conjugate priors, conjugate posterior. So there's an exercise in the tutorial where you will have to do this kind of little computation for the Bernoulli distribution and the beta prior. So that's also quite nice to see that like things work out well if you are in this kind of exponential family. But in general, it's not so hard. Like if you don't know the exact model of the noise of the arms, or if the distribution is not part of a nice family, then there's no reason that you know how to do this Thompson sampling. So yeah, for this algorithm, there's also a very nice tutorial online. So if you're interested in Thompson sampling in particular, I would recommend like there's a tutorial for Thompson sampling. I think it's just called like this, a tutorial for Thompson sampling that's written by Dan Russo, and it's really good. So just to summarize, these are the two algorithms that are called UCB and Thompson sampling that we just saw, and that are basically based on this idea of using uncertainty to make actions. One is really focused on this optimism principle, the idea of, what is the best possible world that I could be living in, and acting optimistically in this best possible world. That gives UCB. And the other one is to use the Bayesian uncertainty to sample from this uncertainty that you have at time t and act in this sampled world for one step. All right. As I said, for the last half hour of the class, I want to show you how these things can work in practice. Other questions? Yes? That's a good question. So like the question is, in optimism, do we bother computing this lower confidence bound a lot? So no. The short answer is no. We don't need a value for like the lowest possible value. We could need it in settings where we are risk averse. Like we don't want to pull an arm that may have a very bad reward, like something like this. Or in setting where actually what we want to do is not really to maximize the sum of the rewards, but at the end of the time, at the end of a certain testing time, I want to output what is the best arm. And I want to make sure that this arm that you return is the best arm with high probability. In that case, you may be interested to try and make sure that like the confidence intervals for, if you have like this arm one here, arm two here, you have the confidence interval here. If they overlap like this, it's not so clear which arm is the best. And like there is a large interval here in which it's possible that arm two is better than arm one. Just following the UCBs will not give you the certainty that arm one is better than arm two. In this case, what you try to do is you try to have an algorithm that is going to pull arm one and arm two more or less until they don't overlap anymore. And once they don't overlap anymore, you're sure with high probability arm one is better than arm two. These are alternative bandit problems or, exploration problems that, people have also studied. It's this type of problems here are generally a little more, they require a lot more samples. You're going to pull these two arms a lot more so that they, the two intervals, they don't overlap. You see in my little videos, it would take a while before these confidence intervals don't overlap at all. But, it's another kind of bandit game, and there's literature on this. So there are two questions. One over here.
Only improving our period with more time samples, but if you want to do something like they take different time predictions and then the period over different predictions,
in Thompson sampling, that's a good question. So is the posterior kind of inflating with time? In Thompson sampling, no, we don't need it. The simple fact that there is randomization no matter what, we never pull exactly the same value for the arm is enough. Why exactly? It's a bit of a magic trick. It's been shown in actually my co-author for this lecture, who is called like Emily Kaufman. So if you search for Kaufman 2012, she proved that actually Thompson sampling has a behavior that can be bounded by the one of UCB. Somehow, like playing Thompson sampling becomes more or less equivalent to UCB if you look at it like the right way, or rather that like there is a low probability that the sample here is above the UCB on the arm, right? So like this would be the UCB. This would be the UCB on the arm. The probability that this happens is actually quite small, just by the nature of the Gaussian posteriors and stuff like this. And so by this kind of reduction, she managed to show that Thompson sampling will behave well, but you don't need this inflation, additional inflation. Yeah.
So when are they most different? You see the Thompson sampling and the trajectories, what is the most different?
So the question is, when are the trajectories of UCB and Thompson sampling most different? That's a very hard question. So I actually don't know. In practice, you're gonna test them. You're gonna test those two algorithms. So in the assignment, we have a nice, I coded for you a little notebook where you can just plug in like the values, like the expressions for UCB and for Thompson sampling, and you will be able to try them out. And you'll see that Thompson sampling is just really, really good. It's gonna pull the best arm even more than UCB. And we saw that UCB is really good. Thompson sampling is just very efficient. And why it's so much better than optimism, we don't really understand it. It's like this is really a fine-grained kind of complex stochastic process question. But essentially, they're equivalent up to minor differences. Yeah. Okay. Take-home message. I think we got it. Thank you. All right. So why is this interesting? So not so long ago, about 10 years ago, some people were, quite excited about games, and especially the game of Go, but generally the idea of modeling the exploration of trees with reinforcement learning, where trees are models for games. So why are trees models for games? I think it's probably quite clear, but just, to give an idea, like if you're in a state, when being in a state means observing, I don't know, like I'm not gonna draw the full game of Go, but like you have like you have a board and you have like things like this. This is your current game, this is your state. And in the state, you have a set of actions. You have a finite set of actions. Right now, if I'm playing black, I can play any of the empty slots. And that's a finite set of action. If I play an empty slot, like here, I move. So these are all my possible actions. I move into the next state. So let's say I move into this state here, which represents this new board. And then there's an adversary who is trying to play against me, that's going to play as well. And I'm going to end up in the next state where I'm going to see a new board of Go like this with exactly the same thing. I'm not going to copy it, but you understand what I'm saying. Why is it an RL problem? Because I am in a state, I take an action, and I observe a transition to a next state, which is actually not a purely random thing. It's someone who is trying to play against me and makes me transition to this next state. And I don't control this someone. I just know that they're optimizing for a reward function that is exactly the minus my reward function. Here it's a zero-sum game. So it's if I win, they lose. If I lose, they win. So it's clear why it's a reinforcement learning problem. At time t, I need to take an action. So in my root node here, that's called root node. In my root node, I need to take an action that maximizes my reward down the line. Not right now. I'm not going to just win right now. I mean, maybe there's an action that makes me win, okay, in which case I should figure it out. But this is like, in this kind of problems, this is not interesting because I can't predict what is my next state, right? If I take an action, I know what is exactly the next state. And if there's one that is winning for me, I know it. It's not a random variable. What is hard to estimate is what is the true value of my reward down the line after many, many time steps. And I don't know if there are chess players or Go players or any sort of board game players in the room, but I'm pretty sure you know that whenever you play a board game, what you try to do in your head is simulate what's going to happen in the future. You plan ahead. You take an action now such that knowing that the adversary is going to play well or hoping that they're going to play well, you're going to end up in that next state. But sometimes this tree or this planning that you're trying to do in your head is extremely hard. First, there's uncertainty on how is your adversary playing, but also just there are too many options. And it's the same for the machine. Digging down this entire tree from the root nodes, exploring all the possible leaves from now and bringing that back to what is the action I should take now in my root node is extremely hard. So what they try to develop, and what they developed is a technique based on exploration and exploitation to explore this tree down the line and bring back an estimate of the reward function of each of these actions, which is going to be noisy. It's going to depend on, the random values of some gains, but like, it's going to give me an idea of what could be the next best move. So how does it work? So MCTS, Monte Carlo tree search, is the idea of planning, but with access to a simulator. So right now, I'm in state S0. And in my state S0, I have, let's say, this finite number of action. And I don't know any of them. So the first thing to do, I'm going to play with my own internal simulator. So right now, I'm not outputting any action, but the goal, this algorithm, the algorithm that I'm trying to output takes as input the state and outputs an action in that state. And what is going on here is a long story. So this is the story of this slide. So what you do is you first try this action, and then you simulate what is going to happen. So you play an internal game with a default policy. So this is going to give you a reward that is random. And this is a default policy. So you play against your own simulator, some random game, some random moves, but that starts with you playing this. And then we see what happens. And you're going to do this a bunch of times. So, like now, let's say that, I've done this a few times. I've explored the tree like this. Okay, so I've explored down my tree. Now I want to know where I explore next. So for each of these actions here, I'm still maintaining a score for each of these actions. So this score, how am I going to draw? I'm going to call it score. So for each of the actions, I maintain the score, which is basically an empirical estimate of how many times I win when I play this action. And I need to go down the tree, select nodes down the tree to refine the value of this potential action. So if an action looks like it's promising, like it has a high score, I want to dig down that tree a little more. If an action looks like it's really not promising, I want to leave it on the side. I don't want to explore it too much. So let's say that, I've explored all these nodes. This one maybe gives me lose all the time. So this is bad. I stop digging it. This one gives me lose all the time. So I stopped digging it. This one seemed promising. So I dug into it a little bit more and I looked at here. Now I'm in the next state. In the next state, same. Here I explored it once and it was losing. Okay, bad. So I stopped exploring it. Now I'm exploring this one. So now, from here, I'm planning this move, this move, this move. And now, question. I don't know what is the value of like down that road, if I do this move and that move and this move, then the adversary does this move and then I do that move and then what next? So I've done some selection here of a path inside this tree. So I've done some planning ahead that seems promising. And I sample another policy. So selection, then simulation. And like this, I continue like this for a long time until I get an estimate of the score of my action that I feel is good enough for me to output this from some function of the score. So the whole process for my algorithm is to dig down the tree. But every time I dig a little bit down this tree, I decide whether I want to dig further or not. And the question is, how do I decide which of these nodes I want to dig into? how do I decide what are the interesting paths inside the tree that could be the next game and that could lead me to win? So this, I don't know if that's like super clear to you, but at root node S0, this problem here is a bandit problem. I have k actions, right? And these k actions have scores, and I want to estimate the score. The problem is the distribution of these scores is not at all a nice Gaussian distribution, and it's actually hard to estimate. And for this, I need to do some planning down the line into the tree. So the idea is to do this selection through an algorithm that's called UCT, for upper confidence for trees. So at the root node now, and for every node down the line, I'm going to estimate their value, and I'm going to follow a max min path. I'm going to select the nodes that have maximum value for me, and the nodes that are minimum value for my adversary. So I'm assuming that my adversary is good, that it's also trying to maximize its own function. So I'm trying to go down the tree following the path of like max min optimization. So when I choose my nodes, I choose to explore the nodes that have the largest min plus an exploration bonus that should look very familiar, which is the exploration bonus that you found in UCB that takes into account this log of the number of visits of the parent. So the current time for this node here, divided by the number of times you actually tried that action. So in every node where it's me who plays, I try to explore a node. I try to go down the tree at a node for which the upper confidence bound is the highest. And my adversary does the opposite, or at least I simulate my adversary as doing the opposite. So my adversary is trying to minimize. My adversary plays in mid nodes, but I need to simulate the adversary's behavior to know where the tree is going to go. So whenever I need to simulate my adversary's behavior, I use the lower confidence bound. That comes back to your question. The lower confidence bound here is used to simulate the adversary's policy. So like this, I go down the nodes that I've already explored and for which I already have an estimate of the score. And when I reach a node for which I have no information, meaning for which this quantity is 0, I use the default policy, right? I sample a random game and I initialize this counter and this counter, right? I initialize a score with number of observation equals 1. Okay. So super easy. I just wanna go through this quickly, just to explain. Yes. Yeah. So that's a good point. In general, the most general way of thinking of MCTS is that you roll out the game until the end. I think you're right that there are stopping criterion that you could use to even like further approximate this reward, and like you would just add a little bit of uncertainty, but given the amount of uncertainty that is in this entire process, you could do this. Even in Go, I think there are also ways of saying, okay, from now on, like it's the end, right? Like, and there are lots of games like this where you can interrupt this simulation.
Yeah, right now, this work if we have a particular space, does it work if I just make a grade and like I still can do the MCQS, or is it not recommended if you have continuous things that you can do? So
the question is, so far it's a non-continuous. It's like a tabular. I have like finite number of boards that I'm looking at, and what would happen if it was a continuous action space? So I'm not sure I have a very good answer to this, but like in general, what is going to happen now is that these boards, they're actually potentially similar to each other, you know. Like for an expert Go or chess player, like a situation and another might actually be extremely similar, and we would like to know this similarity so that the tree has a structure that we can leverage with machine learning techniques to actually estimate what could be the value in a node that I haven't seen if I have seen another node that is actually similar. So you can use machine learning on top of MCTS, and that's the whole AlphaGo magic. That's transitions to the this last part whereby, so okay, now as we said, like for those of you who are familiar with this, sometimes states might be similar, and the idea is to build a neural network that is going to learn this embedding, that's going to learn this representation, and that's going to output for you some sort of pre-value or some prior action probability. So this is this thing. So the neural network is going to be parameterized by some theta. So that's the parameters of the network. And in a certain state, it already tells you what would be prior probabilities over the action and a potential value for this state. So before you've even tried a state, you already have a good hunch. And this hunch, you have it because you've played a lot of games before where you visit other states that were similar, and you can learn it. You can learn this representation. So AlphaGo just uses this additional information, but still keeps this probability, of exploration as a function of, the prior action probabilities and some kind of UCB. So now, the UCB doesn't look so much like we've seen before, but it's still somehow equivalent to 1 over square root n of SA. It's not quite exactly that, I think I don't want to overstate it. What you see is the score function that my algorithm is going to, that AlphaGo is going to use to explore the tree, uses not only the current estimation of the score, which, this thing here actually, incorporates the V, this thing here. So like there is V inside this, but like in a way, like you can, it's like some sort of mixture between V and all your observations as you start seeing observations from this node. But generally, you build an optimistic score for each of the actions in your root node, and you explore the tree like this, using these optimistic and pessimistic values to go through the max and the min nodes, just as we saw before. Now the question is, how do we actually train this neural network? I'm gonna just skip this. Perfect. Well, yeah, okay, I see. Like this last detail that this like AlphaGo is actually using, I think it's relatively important. Once you have like once you stop your algorithm, you still need to have a rule to take the next action. And in all these algorithms, they always use randomized rules. So they sample the next action through a distribution that, that is parameterized by a very fine-tuned temperature Tor. So like eventually, you sample from some kind of, I don't know how to describe it, some sort of distribution over the action that you've estimated from your tree traversing kind of selection function. Okay. Right. So how do we train this neural network? And I'll finish with this. So in AlphaGo, what they did is they took thousands or even hundreds of thousands, I actually don't know exactly how many, of games from, a database of games that are played by humans. So they observed people playing. They had a lot of data of these games, and they fed this to the neural network to train a network to predict this prior distribution over action for every state and the potential value for every state. So for every state of the potential state of the game, you could have, like an estimate of the value that is, learned from all these different games that are in your database. In AlphaZero, they don't do that. They use two MCTS to kind of fight against each other to collect the games. So they generate this large number of games by having two MCTS playing against each other. Each of them are learning the policy that they're trying to optimize their own value function. So each MCTS is going to collect large, sequences of states, policy over action, and rewards, and this data. And every now and then you backpropagate. You give that to your neural network, and you minimize the loss. So you improve the theta that is parameterizing your neural network. And once you have a new theta, you use it for a long time to generate another set of endgames for both MCTS. And like this, you iterate this process. And this is a very known template type of architecture for reinforcement learning algorithm. I don't know if you've already seen this notion of actor and critic a little bit. Well, so like you'll see this for sure. But so in RL, that we have a bit of this notion that like sometimes you have an actor, which is the policy that is currently collecting the data, and you have the critic that evaluates the data that is collected by the policy, and that helps the policy, that kind of updates the actor. We have two heads or two different predictors, right? Two different types of objects, and they interact with each other. And here it's exactly what's happening. We have our critic, which is our neural network that predicts the values of the nodes. And we have our behavior, we have our actors that are the two MCTSs and that are competing and collecting the data, and they kind of alternatively grow each other. It's not easy at all to train a machine like this. And it did require a lot of data. I'm not sure if yes, it's written here. So, it's 20 for each, policy improvement steps. It's 25,000 games generated. And in each of them, I told you that you have to do a lot of this MCTS search. It's 1,600 simulations, right? So for each of these steps, you need to do 1,600 simulations. It's really a lot of compute. It's not a secret that AlphaZero was quite a bit of compute, but required quite a lot of infrastructure and compute. But like eventually, this is the kind of a native start from scratch, go with at the beginning nothing, and just generate your own data and improve yourself over collecting better and better data. Okay, I will stop here just because it's time, but also because I mostly covered everything. So the last part of the course will be on the slides, and I think the slides, do you have them already or not? Yes? Okay. So the last part of the course essentially covers other RL algorithms that use these optimistic principles and these Bayesian principles to improve deep exploration. But they are not theoretical algorithms. There are references, and papers and how people use, things like bootstrap kind of methods, using different heads to generate different potential output for the world, for the different policies, these kind of things. So I encourage you to have a look at the slides and just reach out to me if you have questions. The assignment and the tutorials are mostly about the first part of the class, so you won't need necessarily those things. But if you're interested in reinforcement learning theory, or rather kind of principled reinforcement learning algorithms for which we can have guarantees. This is essentially what my group does. So it might happen, in the future that I might have, interesting topics for you to work on in the group. So, if you're interested to work in this kind of problems, beyond bandit algorithms, but generally on directed exploration in reinforcement learning, feel free to reach out to me. And reinforcement learning theory, like unifying reinforcement learning theory and practice, is still a very much active area of research. It's still not a solved problem. It's really hard actually to design these better algorithms that have provably efficient exploration. So there's quite a lot of interesting questions out there. So yeah, it's going to be your work in the future. And well, thanks.